So we're going to go over the pressure effects let's try that again. So we're going to go over solubility and the effects that pressure has on this. So specifically, let's imagine we've got some liquid like water, H2O, and we've got some gas above it, and we'll constrain the volume. So there's a piston here, okay? A very badly drawn piston. So the gas can only be between the water and the piston, and there's some gas particles with just enough energy to actually dissolve into the gas phase, okay? But if we were to constrain that volume that is pushed down on the piston, in which case we'd be really ramping up the pressure there, that gives us enough energy for these guys to be forced into the liquid phase, which basically means an increase in pressure. So if the pressure goes up, we also see an increase in solubility, or the concentration of a gas dissolved in the liquid. And that results in something known as Henry's law. And Henry's law is stated as that the solubility of a gas is equal to some constant Kh. Kh is something that's unique to every gas. So here's some examples: oxygen, nitrogen, carbon dioxide, and ammonia. They all have different values of Kh based on what gas they are. And multiplied by the pressure of that gas, external. So the pressure is sort of like above the liquid. Right? And that is Henry's law. And we can see that there'd be a linear relationship. One thing to notice about this is that each gas does have its own value of this. And something that is very polar, like ammonia, dissolves into water very easily, so it's got a very high value of this. So let's look at soda in a can and soda after a can has been opened. In a can of soda, the first thing you notice that happens is like you pop it open and a whole lot of gas is escaping. That's because the inside is under a great deal of pressure. So the pressure of gas inside here is about 3.4 atm. And once you open up the can, the pressure of CO2 is much, much lower. It's on the order of 0.30 torr, okay? Which we would want to convert into atmospheres, and that is 3.95 times 10 to the minus 4 atmospheres, okay? So this is the carbon dioxide concentration in regular air and the carbon dioxide pressure inside a can. So the solubility of that inside the can is going to be this. The value for CO2 is 3.4 times 10 to the minus 2. And then the pressure is 3.4 atmospheres, and so this should come out to be 0.12 moles per liter. So that's the concentration of CO2 in a sealed can of pop. Now, if I open up that can of pop, the solubility is very different. So our pressure, our constant is still 3.4 times 10 to the minus 2, but our pressure is much lower, 3.95 times 10 to the minus 4. Okay? That means that our solubility goes down to 1.3 times 10 to the minus 5 moles per liter. So this is a very low solubility, and you might notice that if you leave a can of soda open for a long time, it goes flat. That's because the solubility is going from something very large to something very small. All right? And it doesn't go in reverse. That is, it doesn't become more carbonated as you leave it out. It becomes less carbonated because the pressure has gone down. All right? That's just a simple example of Henry's law.